Good morning, good afternoon, folks. Today I'm going to talk a little bit about segmentation and a little bit about how segmentation doesn't always work the way we think it does. So this is not so much a dig on particular vendors or anything, just a kind of a reality of the world is that things change and you can draw the prettiest network diagram, but unless it's actually accurate, you can't really use it in that sense until you test it. So kind of going all the way back to like late 90s, like I really wanted to work with computers because they're cool, right? You go to these data centers that are like these works of art, like every cable is perfectly in place. It's, cold, it's clean, reliable. There's guards, there's biometrics. It kind of feels like a spy movie. You've got all this really, really awesome equipment. So I started doing consulting work, late 90s, mostly security stuff, but they also had me like racking E450s, for a lot of the companies who were part of the early voice over IP stuff. And it was a really exciting time in late 1990s. Then what happened was the dot-com bust, and so work went from working with lovely data centers that look like this to a little bit more like this. And these are cases where you'd have this beautiful office, you'd have everyone walking around in suit and tie, and yet the server room, telco room is off in the corner covered in trash, dirty, awful. If clients had ever seen the server room or the telco room for this customer, they would have run away screaming because it had, no real relationship to the image that the company would otherwise present. And this is pretty standard. I worked in a lot of these rooms. I had to show up and audit a lot of these places, and this was pretty much the middle tier, and they were worse for sure. Or some of the telco rooms that I had to dig into. Um, so just give you a sense that sometimes the reality is a lot more messier than where you start. And security at the previous place had like a guard and biometrics and all that kind of fun stuff. This place, you basically had a chain link fence at best and kind of a flimsy door, and it was probably falling off the hinges. And the further away the site is you're going to, if you're going to an oil field and you're trying to find like the maintenance room or trying to find like a box where all the radios are, they're not glamorous places, as you probably know. They're places that are do the minimum job they need to do, hopefully at the cheapest cost. And it's a different world than the flashy world of super hyper expensive data centers. So, kind of taking a corollary to that, if you look into the NIST 882 documentation, they provide lots of great examples of architecture, of how far away your enterprise and outside work should be from your controllers, your different Purview levels, and so on. And do a good job of kind of breaking out, like, okay, so you have a human interface device here, control workstation here. Something to keep an eye out though, is anytime you see a device like a remote workstation or control center and HMI someplace, it's bringing with it more than that role. It's bringing with it everything else that goes with that system. So it's not uncommon to find a control workstation that also has a wireless card going to the guest wireless that they can access, so they can actually get on the internet while they have a cable being plugged directly into the operational network itself. And it's kind of a given, right? You don't expect people to go into these rooms in these areas to be able to do work completely offline. And oftentimes you have to have some other way to get back to the internet. And, so people take shortcuts at some point. So it's not uncommon to see a device sitting on a desk that has, a mobile LTE thing, maybe a little hotspot attached to it, maybe a, remote dial-in modem and old Digi International. And those are the types of devices, the types of exposures I want to talk about today. So with anything in 882, there's a ton of caveats. I think I counted like 68 different caveats and callouts in the document, which are we want you to do X. However, the real world says this, this, this. So for example, they have a great call out for zero trust. Hey, some OT components may not support any of the ZTA, ZTNA technologies at all. That's normal. You're going to have to just isolate them. You have to do other things around them. But these limits apply to every part of the chain. So I was digging through docs and trying to figure out like what is the number one control that's actually used to segment systems? Like how do we actually make segmentation? And the short answer to that is firewalls. Firewalls are the number one way to isolate things, and that sounds obvious, but when you start looking at these diagrams again, the firewall keeps showing up in deeper and deeper and deeper places for the organization. And keep in mind, somebody actually has to be able to manage that firewall. So when you look into a network and you're like, okay, well, what is the most sensitive thing in the entire environment? Is it the HMI? Is it the SCADA control system? Is it actually like the IO server or Storian? No, often it's the admin control for the firewall itself, because the firewall is what's enforcing all this access. And if you had access to, say, the firewalls, you're able to basically, go through every level here, access anything you want. And that's kind of the holy grail for attackers. And we've seen attackers pay a lot of attention to this, especially in the last 2.5 years. We used to look at these devices being kind of the way to protect our environments. But now they've actually become the number way into these environments for attackers as well. So we often talk about, okay, well, attackers may use the side door or the back doors or whatnot, but at the same time, they sometimes just use the front door. So in this example, earlier this month, or sorry, early in January, CISA put a note out about another round of vulnerabilities in some of the FortiCloud products and auth bypass for some Fortinet products. This is normal. Like everybody's got vulnerabilities. Everyone has, stuff in their code that could work better or they get exploited by actors. But what's kind of notable here is that firewalls are the main control. And if firewalls go all the way down to your level two, and they have things like authentication bypass bugs, they're probably accessible from the higher levels, and they're probably also able to reach down to the lowest levels. So you've taken your entire, segmentation stack and really made it a single control that doesn't fail very well. And it's not just in this case, Fortinet is the example that I picked here from the website, Pacific Great Image, but really every other vendor in this space has been really in this targeting errors for state actors for the last 3 years straight. So Mandiant did a report last year looking back at a full year of incidents that they had to go on site and do incident response for. And in those incidents, there were four initial access vectors that were exploited the most. So there are many other ways people get into these networks. You can do phishing, you can do other insider attacks. But I think about the 30% of all the incidents they investigated start off with initial access. And of those, the top four entry points were Palo Alto, Avanti, and Fortinet. So, we've done a good job of making these products a very key part of our OT security deployments. And the attackers have now done a really good job of turning that to their advantage and using them as, the stepping stone to get into the environment. So, a lot of folks talk about, do they need to go around the side door? Do they need to find some kind of weird, squirrely thing off on the side? Is there some OT specific risk? No, you just use a Palo Alto 0 day and you walk right in. And that's pretty much the case for a lot of these breaches that we've seen. So I want to talk about some of the ways that uh, the kind of OT network segmentation struggles. We talked about how firewalls are really, often the front door for attackers, especially if they're out of date or there's the 0 day going around, or if the company just has a history of having, exploitable products. But firewalls can't help you when you have other devices on the network that allow attackers to go around them. So, in your lovely diagram, you assume that everything in the stack here has to go up and through the firewall. But what actually happens is a lot of these devices have multiple connectivity points. You may have a workstation down here that has a Wi-Fi connection to a different segment. You're supposed to be isolating these pretty levels, but the reality is people don't. They've got crossover cables, they've got out-of-band management tools, and those things allow you to jump directly from layer to layer to layer. So going into bridges, this is something that I love playing with. It's one of the things that I work on all day for fun at my job is being able to identify a device that is acting as a router or could act as a router even though it's not intended to. So just about every printer, television, storage device, laptop, light bulb, these all support connections to multiple different networks at a time. So your typical iPhone, if you pop it up and look at the settings, you've got about like 19 different interfaces out of the box on it. Now, going and looking at something like a Mac laptop, like I just did a quick count last night. I've got 28 different live interfaces on my Mac laptop. And it's not that complicated, right? It's just sitting on my desk. It's plugged into an Ethernet port, but it's also plugged into or connected to the wireless network. And this is incredibly common. We used to go from environments where you have maybe one Ethernet cable, maybe two Ethernet ports, maybe Wi-Fi plus Ethernet, to now laptops shipping with mobile WLAN adapters, being like cellular connectivity. In this case, the Mac laptop supports like display link protocols, all these AWDL stuff. It's got a bunch of tunnel adapters on it. And it's just got a lot more complicated. So it's you will actually struggle right now to find a device that you use every day that does not have between 5 and 25 different interfaces active at a given time on it. It's no longer you type ifconfig and you see one thing. So if you're curious about that, like if you have a Windows laptop, just type ifconfig, take a look at it. Like what is in there that you don't expect? Like obviously you see a lot of things like IPv6, but you see a lot of tunnel adapters. You see a lot of these like alternate paths in, and those can all be avenues for an attacker to get into the network. So we did some research a while back about how many of these devices not only bridge, connect multiple networks together just by definition, like a laptop that's on the, production network Ethernet, but is also on the guest Wi-Fi. That's a great example. How many of those devices are configured that way, but are also just doing plain old packet forwarding? They've actually had IP forwarding turned on specifically in the operating system, where somebody can just use them as a router and go with no attacks, no pivoting, no amount of like exploitation required. They literally just connect, set you as the router, and off you do the thing. And we found thousands. We found that thousands of devices out there, everything from like Synology disk stations to West Digital Storage to just about every printer you can imagine. A lot of like the ESP32 kits that drive like light bulbs and smart TVs and things like that, they all have forwarding on by default. We actually had a harder time finding devices that did not have it on by default. In some cases, workstations would have otherwise been fine, except for then the developer or the admin installed something like Kubernetes or container system like Docker. And as part of installing Docker, not only does it create a ton of virtual interfaces, but enables IP forwarding on all your interfaces. And it may not occur to the user that they now need to go manage a multi-interface firewall, which is their own laptop. So what happens is that a lot of folks will have bridging enabled on their systems. They can accidentally bridge networks that are different security levels, and it's really difficult to find these, of course, because this is not something people are typically looking for. So if you start looking at how these connections scale up, there's like the 7 degrees of Kevin Bacon. You try to see like point A to point B to point C. So this graph here is about 30 employees in network. That's how complicated it is already with maybe 30 people. These two red dots, these are actually external facing IPs in this network. And there's often more than one, and folks generally don't know about at least one of them. And there's a lot of reasons for it. We'll go into a little bit later. But once you start scaling up to a couple hundred employees, let alone thousands, it turns into one big hairball. You've got cross connectivity from network to network. If someone's able to compromise a particular network switch, well, network switches are actually how you enforce your segmentation. So if there's any path to get into your network switching hardware, any path to get into your firewalls itself, they now own all your segmentation. They can now go from any point they want to get to. So it's a little bit more fragile than a lot of folks realize. All it takes is one device with more than one cable with more than one connection to basically route between Purdy levels with no filtering. And of course, that traffic does not go through the firewall. It doesn't show up in your normal monitoring, and it's not a choke point. So this just gets more and more difficult to do right the bigger your network is. And once you start crossing into like thousands of employees, it's just one big hairball. You can effectively go from any point on the graph to any other point on the graph in like one or two hops at the most. It's really like the 1 degree of Kevin Bacon once you've gone to a particular level. And this even includes OT remote sites. Even an OT site that's, a building in the middle of the desert, you may see two or three different external internet points. You may see five or six different ways to jump between Purdue levels that are not intended mechanisms. And that is absolutely normal. But again, it's not something that folks are actively auditing. We tend to treat segmentation as an issue that you do as part of your design flow, not as segmentation as a thing you're constantly trying to audit all the time. So this is, not the only thing I do all day, but it's something that I think is underknown and under kind of recognized as a risk in the field. So another category of kind of exposures that a lot of folks don't take into account are all these out-of-band management devices. So I love seeing a Moxa or a Lantronix hanging out of the network because those are absolutely the worst. You take a device that might have had good security to start with, you hook it up to a serial port or a KVM port in some cases, and then you put a device that definitely has bad security at the head end for it, used as the management system for it. And oftentimes that Pi KVM switch, that Lantronix, that Moxa, it has worse security than the device that it's supposed to be protecting or providing remote access to. In some cases, like Digi, they invent their own protocols. They've got a real port terminal discovery protocol that I did a bunch of research on back in the days with Metasploit, and we found just a ton of ways to basically access the sessions of those things remotely without credentials, and just kind of boneheaded bugs that you'd find in consumer level electronics are also present in a lot of these enterprise/industrial KVMs and out-of-band systems. And take that further. If you've got a server that has an HPI-LO, Dell DRAC, any of these remote out-of-band access control systems like the IPMI and a Supermicro, for example, those are terrible by default. Even with the new law in California saying that every Supermicro has to ship with a default password, with a no longer default password that's not hard coded. They ship now with a password based on your device serial number. They still ship with IPMI enabled by default and RACP plus enabled by default, which allows you to basically just dump the users, dump the passwords remotely, crack them, and log right in. So we haven't really gotten that far. We still have a world where the default security of our out-of-band management devices tends to be much below the security of the devices that we're actually protecting. So attacker doesn't have to go after your very secure server or very secure workstation. They typically just have to go after the Pi KVM or the Digi International or the Lantronix, and those devices are typically much easier to access. So the last category I want to talk about just roughly is IPv6. We've been asking about the year of IPv6 for a very long time, but we've been there for a while. It's not that we're IPv6 something that we often think about. It's just IPv6 is already everywhere. Again, looking at my local laptop or even looking at my iPhone, if you do an ifconfig and look for interfaces that are link local addresses attached to the adapter, you have a ton. You have something like 20 to 30 interfaces that are v6 active at all times on your network. And those interfaces, they act like normal IPs. You can scan them, you can connect to ports. If you have a device that uses IP tables to filter traffic and they forgot to do IP tables on the v6 side versus the v4 side, you often end up with a device that has, a pretty good bill of health on the IPv4 address. But if you're in the same link local network as it and you scan it on its v6 address, you see a whole different set of things. You see things like Mongo database being directly exposed that a credential, Redis servers being opened directly. You see NFS servers exposed through v6. So, it's pretty easy to get it wrong. If you have a device that has v4 enabled and you don't really think about the v6 side, it's easy for that to be kind of a backdoor that you weren't aware of. Now, on the external side, Shodan has been doing kind of the good work in that sense of helping folks identify how much of V6 is actually exposed to the internet. Now, you can't just like scan a V6 range. You can't just say, I want to start with zero and then go all the way to dot FFFFF because it would take forever and you'd never actually make a dent in it. So instead, Shodan uses things like DNS and some other kind of controversial stuff to go to a list of V6 addresses and scan them and keep track of them. So for example, if you're using the ntp.org time infrastructure, which many of us do, whether we mean to or not, because all of our devices, all of our routers, all of our systems go back to NTP. If one of those devices is on IPv6 and makes a connection out to NTP, you're eventually going to hit one of Shodan's time servers. So Shodan actually runs, I would say malicious, but they're definitely not in your best interest time servers that will actively give you the time, but they will also keep track of your IP, port scan it, and put that into a giant list on the internet you can then search. So we've gone to the point where there are very, very few IPs on the internet. There's something like, yeah, sorry, V6 IPs in Shodan. At one point, there's only something like, maybe 2, 3 million. Um, but after they cranked up this NTP-based discovery mechanism, Shodan was reporting something like over 200 million V6 addresses at a given time. And you can be sure that most of the owners of those addresses had no idea this was happening. I was working with a customer just last week, and we had a reporting in the product saying, "Hey, this device has a public IP." And he's like, "I looked up and down. There's no public IP in this thing." I'm like, "Yeah, it's right. It's right there. It's V6 headers." He's like, "Why is my IDS? This is supposed to be a packet capture link, by the way. This is a span port on a device that was sharing the span port with the upstream router that was providing the traffic going to it. But that upstream router was actually providing global V6 addresses to all systems on the same subnet. So it didn't occur to this gentleman at all that his supposed to be super secret IPS server, IDS server that's capturing all this traffic was in fact actually globally reachable through IPv6 through an IP he'd never seen before. And these things can change on you. There's at one point where Comcast rolled out a configuration change to their customers where all their all their existing routers in place started advertising global IPv6 addresses behind the firewall. So if you're behind the router, now every single workstation behind it has a global V6 address that's reachable on the internet that does not go through your normal filtering. And this is fairly common. So keep an eye out for V6, both the link global variants, where these provide alternate paths to the same services on a given interface, but also global variants, which can be automatically assigned by an ISP in a way that you're not often to be able to detect easily. So that kind of takes us to, where are we, right? We've got our view of the world in terms of like ideal state, where things should be connected, where they're, where our controls are actually in place. And then we have the reality, which is way more messy. We've got, just people dropping hardware, forgetting about it, misconfiguring it. We've got cell modems that are just plugged into a wall as emergency backup lines that folks have forgotten about. We've got great segmentation, which is then completely destroyed by having a firewall that's remotely exploitable. And just a lot of different variants where the things that we rely on to protect us in terms of segmentation and controls are undermined by these kind of normal day-to-day kind of small breaches here and there. And yeah, it's a lot. The tricky part for this isn't that they exist; it's that how do you go find these things? You're not going to run a vulnerability scanner. Your vuln scanner is not even going to tell you about this stuff. Because vuln scanners are looking for things like, did you patch this vulnerability? Is this firmware out of date? Most of the time in your OT environment, of course, it's out of date. You're not going to apply an update to it. Like, it's fine. But what does matter is figuring out whether that is unauthorized connectivity or some way around your segmentation. And that's where you have to take kind of a different approach to discovery. So I want to talk a little bit about like how you actually go and find this stuff. Like, how do you actually identify the device as multi-homed when you don't have direct connections to it? And first by preface saying that most of the tools in the space have been passive discovery for a very long time. And that's great when it works. Typically, you would install a device that can capture traffic. You connect it to a span port, and you have it just looking at the traffic going in or out of the environment. And theoretically, if something's compromised or something dodgy is happening, you'll see traffic beacon out, and you say, "Aha! I got somebody. Here's their C2. Here's how they got in, etc." There we go. That doesn't really work so well these days. The reason for that is you're often not getting span port captures close enough to the end equipment to see the stuff. You're not getting like link local lookup request on the kind of bottom layer at your pretty level two or whatnot. You're usually just seeing north-south traffic, not east-west traffic, depending on your deployment. So granted, there's ways you can expand your passive traffic to get better visibility, but kind of by default, you're not seeing anything at that level. And again, the more individual sites you have and the further apart they are, the more expensive it is to really deploy packet captures across the board. So what do you do instead? The short answer is active scanning. And active scanning has been a swear word in OT for a very long time for a lot of really good reasons. I've got a long laundry list of things that have fallen over, broken, crashed, endangered human safety because somebody ran Nmap and pointed to the wrong IP. And so you can't just take Nmap and throw it at stuff and be like, okay, now tell me about this stuff. And also Nmap and even tools like Tenable, they're not particularly good at telling you about whether a device is multi-homed or not. They're good at telling you whether a vulnerability exists or a patch is missing, but that's it. So that's kind of where I spend my time. I play around with a product called Run Zero. We got a free version, community edition, all that fun stuff. So you're welcome to play along at home. Um, and let's talk a little bit about how we go about and do this. So typically in the product, we've got your standard dashboards, you have a list of all the stuff we found over time. We've got a kind of a deployable explorer, and these explorers can be deployed anywhere where you've got, Windows machine, Linux machine of any flavor. We've seen people deploy these explorers, everything from a NAS storage array to a Raspberry Pi to an embedded container on a router already. If you're using things like IOX, the explorers are fairly small, and anytime you've been able to deploy one of these points of presence within an environment, you can then use that for passive capture, whether it's full-on span or GRE or encapsulated traffic. But you can also use it for active scanning. And active scanning is a little bit different in Run Zero than you look at something like a normal vol management tool. So, for example, we care a whole lot about safety. We care a lot about making sure that we don't trip anything over. And so we've got different safeguards, like we'll set a maximum host rate, packet rate for each individual host to make sure we never go above a certain wire rate. So if you want to say never send more than 1 packet per second per target, great, here you go. And the maximum host rate also applies to broadcast traffic. So it's a great way to kind of filter that out and make sure that you're not overloading, Zebra printers with the broadcast traffic on the back end. So lots of options here. I don't want to get into it too much here, but I do want to talk about how some of the neat stuff works. So if we go into normal environment, this is kind of our local network here. You'll see that for IP addresses, there's a whole bunch of little plus signs. So this particular IP, you see it's not just .1 for one subnet, it's all these .1s. This is an open sense router that drives the main connection for this environment. So every VLAN is split off, every VLAN's got a different firewall IP. But we're telling it right off the bat that this device is actually a critical part of the network because it has so many IPs associated with. So here's another example of where IPv6, we've identified the v6 link local. And so okay, I can target this device on 10.1.1.4.128, but I can also look at the v6 side. So if we go all the way down to the actual services on this device, and let's find an example and find a better one real quick. But typically, if you find one that has both v4 and v6, you can start seeing a little bit of a difference between what services are exposed on one side versus another. So let's see, look at the v4. Oh, that was not a lot of v6 on that side either. Firewall. So obviously for the firewall here, you can see it's got different ports open per interface. You can see DNS, things like that. Not super exciting, but it does kind of tell you that, it's able to tie all these different interfaces back to basically the same asset. So if you wanted to find other assets that have unexpected v6 addresses, there's a few ways you can do it. In this case, here's a kitchen speaker that happens to have two different link local IPs. One of these is used for the Google Home automation stuff. Another one's being used for normal link local traffic. So if we start digging into, for example, this asset, and are we in the services side? There we go. So in this case, you can see for 30.37 IP, you've got a set of ports. You look at the separate one over here, and you got pretty much the same list of ports. So nothing too exciting here. But oftentimes what you'll see is that the v6 IP has a bunch of ports open that are not open on the v4 side, and sometimes vice versa. So it's not uncommon to find like a telnet port open on v6 that was not open on v4 at all. In terms of how you go about and scan this stuff, it's a little tricky. So assuming you only have connectivity to a single port on the network at once, we'll do things like convince the device to tell us about a secondary IP. So for example, we search for epm.name. This is an attribute that we set in the scan based on finding let's see, host name, I believe. There we go. So this is an attribute we attach to an asset after we're able to connect to a port 135 TCP unauthenticated. And what we do for this is we actually send some queries to it to have it tell us what its other IPs are. And this is all unauthenticated over the wire. So we go down to our 135 TCP. Here we go. You can see all kinds of stuff comes back. We get a big list of profiles, you get a big list of all the running services on it. And this is all unauthenticated off the wire. And here you can see right away that 10.1.1.4.1.2022 is the IP, and here's the host name for it. So this device is on more than one network at a time. We'd see a long list of all the different adapters, especially things like V6 global unit or unicast adapters would show up here in the EPM route. So the cool thing about this is you can actually just point and shoot and find devices that have a VPN installed very quickly without having any endpoint access to the systems. So just by looking for a device with more than one IP address, you can quickly identify machines that have been wired to misconnect or cases where it's got an IP in one network, but also another network. So in this case, we'll search for let's see, has public. Always a good example, always a good thing to search for. Does it have a public IP at all? We'll search for true. And so here's some standard public IP stuff. Okay, that's mostly well known. But what about this guy? It's got a 10.114.133.7 IP, but if we dig into it, it actually also has a 203.0.112 IP. So this device is directly attached to the internet. It's also directly attached to our internal network. And in doing so, we now know that there's probably a path from the internet to this system. And if you look at the vulnerabilities that are found on it, we actually say that. We say, hey, there's actually some risk of this device being directly exposed. And the way that we do this in this case is we actually look at the overall, we basically scan the entire internet ahead of time. We build a big cache of all the observed TLS certificates, SSH host keys, unique device fingerprints, things like that. And then we look for on the internal network, a unique, calculate the same hash, the same fingerprints, and then we do a lookup against it. So you can scan an internal machine, know absolutely nothing about how it's connected to the internet, and be able to figure out where it's exposed in the internet in one shot really quickly. And this is really cool. It's actually like instead of having to start on the internet and figure out how the device is associated with a particular asset, you start off knowing exactly where it's exposed and exactly where it's attached to it. So just kind of a quick shortcut. And all this does is basically correlate TLS certs, unique identifiers from network A to network B. So I know we're short on time. I do want to make sure we've got time for questions. But if Run Zero is a lot of fun to play with, we find all kinds of stuff. We can find secondary interface in nearly anything. It's usually safe to run anywhere. We've got a kind of out of the box safe profile. And we did some work with the DOE as part of their SECA program to test in a real live transmission and generation network and verify that yeah we find all the stuff in the network and that we don't cause any issues. So with that, I'd like to ask folks for questions.
Fantastic. With the 1 minute we have left there, we got one question that's bringing it back to your first slide. You talked about the 90s and data centers in the 90s and so on and so forth. So this question kind of comes from that era, but relates to today's content because the debate apparently is still very active, and this is it. From your perspective, and great presentation and demonstration, by the way, there's also a link now to Run Zero in Slack. So the question is this. Do you believe that multi-vendor firewalls are meaningful today, as it was in the 90s, to reduce the capability or possibility of exploitation of the first firewall and the next firewall if it's a different vendor? Is that still something that is, from your perspective, a debate, or is it just, yeah, have two different vendors? Because you showed that there are firewalls that have vulnerabilities, and if they're not tended to, as your point mentioned, was if an attacker owns the firewall, they own the network. So do you still think today that's a relevant conversation of two different types of firewalls and perhaps between IT and OT as a primary defense?
It's a good question. On one hand, I'd like to say you can layer like a checkpoint with a Palo Alto with a Fortinet. On the other hand, like any given week or all three of those can have vulnerabilities at the same time.
Yeah.
Like, so the challenge is like, unless you have, I would almost say like, just build a bespoke, OpenBSD, FreeBSD Linux box and use that instead. I mean,
It's
sure, have
awesome.
a Fortinet somewhere too, but have something else in front of the Fortinet. Like when we saw the big rash of like firewall bugs start to come out 2 years ago, a lot of the vendors said, oh yeah, to protect our checkpoint appliance, buy another checkpoint appliance, put in front of it. I'm like, okay, it's probably not gonna be a checkpoint. We'll put something there.
Right. Excellent points on this. So the layering helps, but I think what you also pointed out is that the firewalls need to be maintained, and dare I say patched, but they need to be maintained so that it's not easy to bypass, as you've described and pointed out with those exploits. Thank you so much for your time today. HD Moore rocked it today. Thank you very much. And if you have any further questions, please drop those in the Slack there. Thank you again for joining, sir.
Well, thanks. Yeah, see you in the Slack. Thank you. Bye.